Hello, good morning, good afternoon, good evening. This is lecture 1 of ComSci 123, Data Structures and Algorithms. Before we start, I will just give a small disclaimer. So I'll be doing this recording in one take. I won't be pausing or editing this video. So if you hear me cough or stutter or have a long pause somewhere in the middle of the recording, please excuse me for doing so. Okay, so let's start. For today's topics, we will be introducing data structures and algorithms. We will also talk about some object-oriented concepts that we need to understand some implementations of data structures later on. Now take note that this will not be a detailed um, treatment of object-oriented concepts, so this will only be an overview, and I will leave it to your ComSci 22 object-oriented programming class to discuss the details of these concepts. Okay, so let's start with object-oriented concepts. And the reason for discussing this first is because the data structures later on, we will see that they use the concept of abstraction versus implementation. And there's also the concept of inheritance. Okay, so to start, the basic building block of object-oriented programming, or OOP, is the class. So a class is a blueprint. So it defines all objects of that certain type or class. Inside the class, we define properties and methods for the objects of that class. So examples of properties would be person.name, person.age, right? So properties are like information. Examples of methods would be person.talk and person.walk. So these are actions or methods. Okay, so the class is a blueprint. Now, objects, on the other hand, are instances of a class. So we create specific objects from a certain class. Objects have identities, so they have an object ID. We can distinguish one object from another. We can check whether this object is the same as another object. And an object also has a state, which is defined by its properties, and behavior, which is defined by the methods. So those are the two building blocks of OOP, classes and objects. Next, we'll look at some of these OOP principles, namely encapsulation, abstraction, information hiding, and inheritance. First, we'll look at encapsulation. Encapsulation is all about this. So encapsulation is about keeping the data and operations in the same place, which is in the object. Okay, so inside the object, you keep all the data and all the operations in one place. Unlike, for example, if you don't do it in the OOP way, you could have three variables for, say, name, age, and gender. And then you also have one function for talk. So there are four separate things. So you have three variables and a function. But in OOP, all of that will be inside the object. So your name, age, and gender will be properties of the object, and talk would be a method of the object. Okay, so that's encapsulation, keeping everything in the same place. Next is abstraction. In abstraction, what we do is we only show the essential parts of the class and we hide the unimportant details. So an example of this is a roadmap. A roadmap is an abstraction of the actual road. Why is that? In a road or in a roadmap, you will only need to draw, let's say, whether the road bends to the left or to the right, or is it straight, what's the scaled distance, right? Is it 1 kilometer or 2 kilometers, and so on. So you only need to keep the essential parts. The unimportant details, like whether the road has bumps or whether it's made of, let's say, asphalt or cement, that's not included anymore in the roadmap. So you only keep the essential parts and you hide the unimportant details. For classes, the way that they do abstraction is by using something called an interface. The interface is a set of methods that the object supports. So what this means is you list or you define a set of methods that each object will um, will be able to support, or you can call that method for all objects. So it's like a contract. So even if I don't know the inner workings of that class, I know that this method can be called for that object because it is part of the interface. Okay, so you only expose the essential parts or the needed methods, and you hide all the details within the class. So that's abstraction. So as I've said, the classes only expose their interface and they hide the implementation details. So later on in our lab exercises, we will see an example of this. So halimbawa, si array stack and an SLL stack, they both follow the stack interface. So if we use an array stack or an SLL stack, it doesn't really matter. They have a similar usage. So they have the same methods because they all follow the stack interface. However, they will have different implementations because one is using an array and the other one is using an SLL. Okay, so we don't know about the implementation details, but we know that their interface follows the stack interface. Okay, that's abstraction. Next is information hiding. For information hiding, we try to keep the properties or instance variables private. And the reason for that is because we don't want other objects or other classes to be able to access these properties directly. So to get around that, we will use public getter and setter methods to manipulate these properties that we have set to private. So this is actually mostly true in Java, but not so much in Python. So we will not dwell too much on this. And later on in your ComSci 22 class, you will learn more about private properties and getter and setter methods. So that is part of information hiding. Okay. Next is inheritance. So inheritance is a way to organize your classes into a hierarchy in order for us to reuse some of the code. Okay, so in inheritance, we have something called the superclass, which is like the parent class. And in the superclass, you define generic properties and methods. So when we say generic, it applies to all classes that inherits from it, right? And then under the superclass is the subclass. So the subclass will extend the superclass and it will define properties and methods that are specific to it. Okay? So for code reuse, the subclass can inherit the properties and methods of a superclass. So once a subclass extends the superclass, everything that is part of the superclass will be inherited by the subclass. So we'll see that in an example in the next slide. And another thing that the subclass can do is override the methods of the superclass. So it could also specialize some of the methods, especially if it does it different from the way that the superclass does it. Okay, so let's see a concrete example of that. So for inheritance, We have the person class as the superclass and three subclasses, namely the math teacher class, footballer class, and businessman class. So the person class has three methods: talk, walk, and eat. So because the person class is the superclass, all three subclasses will inherit these three methods: talk, walk, and eat. So the math teacher can also talk because it's also a person. The footballer can also walk because it's also a person. And the businessman can also eat because it's also a person, right? The subclasses, on the other hand, have their own specialized methods. Like, for example, the math teacher has a teach math method that is only specific to it. A footballer has the play football method, which is also specific to it, and so on. Now, later on, we might also find that we might want to override some of the person methods. Like, let's say maybe the math teacher um, talks differently because, let's say, the math teacher talks fast. So we could override the talk method and define another talk method inside the math teacher class. Or let's say the footballer walks different from a normal person because of an injury, maybe, or I don't know. So we could also override and redefine a walk method inside the footballer class. Okay, that's inheritance. So our goals when doing OOP are the following. So we have three goals. Number one is robustness. So we want our code to be robust. So we want to produce correct solutions and gracefully handle unexpected input errors. So it must not only be correct for correct inputs, but what if it has wrong inputs, right? So unexpected input errors. So as an example of that, what if we try to remove from an empty container? There's nothing to remove, so it should be an error, right? So we'll learn more about that later. So our code should be robust. Next is reusability. So our OOP code should be able to be used as a component of different systems in future applications. So it's not only used in one app, but maybe it's also used in another app. So, and as an example, uh, later on in lab number 3, we will be implementing the array and SLL node classes. And these two uh, classes are actually very important because we will be reusing them for a lot of the next exercises when we implement other abstract data types. Okay, so that's reusability. And finally, we also want our code to be adaptable. So it has to evolve over time and adapt to changing conditions. And it also must run with minimal change on different platforms. So it must be portable, and it must be easy to maintain. And by using OOP, um, it actually improves the maintainability of your code because it's not spaghetti code. It's not mixed in, right? So most most of your code probably in the past are very uh, jumbled and messy. But if you write OOP, it will be pretty organized, I would say. Okay, so that's um, the goals for OOP. So to review, encapsulation is all about keeping your variables and methods inside one place, which is the object. So think of the capsule wherein everything is inside it, right? And that way we could also hide the information that we want to keep private. Next is abstraction. We only need to focus on the important parts and not worry about the unimportant details. So for example, as a cat owner, you only need to worry about feeding the cat or like petting the cat, and not necessarily worry about, let's say, the cat's anatomy or whatever, right? So if it's unimportant to you, abstract it away. And finally, we also talked about inheritance, which is a way for you to organize your classes in such a way that there could be code reuse. So for your super class, you put all the generic methods and properties that will be inherited by the subclasses. And the subclasses will inherit those, and they could also override some of those methods if they want to specialize. Okay, so that ends the object-oriented concepts part. Let's now move on to the data structures. So first, we need to talk about data. So what is data? Data is information, right? It could be input information or output information. So that's data. Now, what are data structures? Data structures are a systematic way of organizing and accessing data in computer memory. So it's two things, right? You organize and you access the data in memory. So that is the purpose of your data structure. And it's important to use the correct data structure, because if you organize the data in a good way, then you will also have better and efficient programs. Because if your data is randomized or scattered or unorganized, the program will probably take a longer time to process everything because it's not organized, right? So that also applies in real life, right? So that's data structures. Now, for any data structure, we need to ask these two questions. Number one, how are the data related? So this talks about the organization of the data. Okay, so as an example, are they in a sequence or are they in a random order? So that's the first question. The second question is, what operations can we do on the data? So this is about accessing the data. So what can we do with the data? How can we access the data? So as an example, could we add or remove data, right? So moving forward, for each data structure, we need to ask these two things. How are they organized and what operations can we do? So how can we access the data? So as an example, we have the stack data structure. We'll learn more about this in 2 weeks time. So the stack stores items in a last in first out or order, uh, LIFO or LIFO. So last in first out, and it supports 5 operations. So you have the push, so you add an item to the stack; pop, which is removing an item from the stack; top, which is looking at the top item of the stack; then size, of course, how many items; and then is empty, whether the stack is empty or not. Okay, so 5 operations. So yeah, this answers the 2 questions. How is it organized? So it is in last in first out order, and the operations it supports are these 5 operations. Okay. Now later in the class, we will also hear about this term abstract data type. So what are abstract data types? It is just a specification of a data structure. So a specification which contains, number one, the type of data stored, and number two, the operations that are supported. So it's also kind of like a blueprint in a way, right? So we list the operations that are supported, but we don't specify how to do it. So we don't specify how to implement um, the operation. So that's why it's abstract, right? So the abstract data type is an abstract interface. So it only lists the methods that are available for this ADT. If you want a concrete implementation, that would be your data structure. So a data structure is a concrete implementation of a abstract data type. So to implement it, you write a class, and inside that class, you implement the actual methods that are part of the ADT's interface. Okay, so again, abstract data types are abstract interfaces only, so it only lists the methods, whereas a data structure is an implementation of the ADT, so you have the actual implementation inside. Okay, so that's data structures and abstract data types. Next, let's talk about algorithms. So you probably heard of this term a lot. What are algorithms? An algorithm is a step-by-step procedure for performing some task in a finite amount of time. So you've been using algorithms ever since you've started your ComSci life, probably, right? Or even before that. So algorithms can be written in natural language. So for example, step one, um, you do this. You take out the food from the fridge. Step two, you eat the food. Step three, you wash the dishes. So that's an algorithm too. It's a step-by-step procedure for performing some task. You could also write an algorithm in pseudocode, just like this in the previous slide, and in actual computer code. Okay. Now, how different is an algorithm from a program? So sometimes these two terms are used interchangeably, but there's a proper usage for each one. So a program is an instance of an algorithm, and it's written in some programming language. So an algorithm is like abstract also. So it doesn't have a specific programming language, whereas a program is an actual implementation of the algorithm. So the concept of abstraction versus implementation comes back again, right? So one algorithm could have multiple similar programs. As an example, the hello world algorithm, wherein you print hello world, that's it, that's the algorithm. There could be three or more different programs for it, like hello world.java, hello world.c, hello world.py for Python, right? So algorithm is just one idea or one set of steps, but a program is an implementation or an instance of that specific algorithm. Okay, now why do we need to study algorithms? Why is it important? Number one, it's because we need to solve problems efficiently. So if you have a good algorithm, then you will have an efficient program. And if you have a bad algorithm, of course, the performance of your program will also be poor. So as an example, you have sorting algorithms. So if you have a good sorting algorithm, like let's say merge sort or quick sort, heap sort, and so on, then you can finish sorting, let's say 1 million items, right? It can be done fairly quickly. But if you have a very bad sorting algorithm, like let's say just uh, let's pick a specific example. Let's say we want to sort a deck of cards. Let's say so there are 52 cards, right? So the most basic way to do it is probably by insertion sort, by picking each card one by one and putting it or inserting it into the right position for the cards that you've already processed or have seen. But uh, a stupid way to do it is probably just like taking all the cards, throwing it up, and picking it back up, and then hoping that it's already sorted. So it will probably take you a long time, and it will still not be sorted because you have a very bad algorithm. Okay, so Good algorithm is equal to efficient program. Now, what else? Why do we need to study algorithms? We also need to analyze the correctness and resource usage of the algorithm. So next meeting or in our next topic, we will discuss analysis of algorithms when we do exactly this. So we'll analyze how much resource is being used by the algorithm. Why is it slow? Or why is it fast? Or why is it taking too much memory? Okay. Next, computation is also fundamental in many fields. So computation is not only used in ComSci, in computer science, but in other fields as well. So for example, in biology, you have your um, bioinformatics, in other fields as well, like chemistry, mga uh, genetics, and so on. So it's not only in ComSci, right? So even in other fields, there are a lot of algorithms that exist as well, even in speech processing, in computer vision, and so on. Okay, and finally, some giant tech companies started with an algorithm. So, for example, Google, we all know that it started because of the PageRank algorithm. So, who knows? Maybe one of you will be really interested in algorithms, and in turn, it becomes the start of a tech company that becomes big later on as well. So who knows, right? So yeah. Now, for a programmer, he must always aim to do the following. So number one, design efficient algorithms. So I don't know if any programmer would want to design an inefficient algorithm, right? So everyone wants to do it quickly, or to do the task quickly. So we want to design it to run efficiently as well. And the programmer must also analyze the algorithms to prove that it is correct and to estimate the needed resources. So we can't just claim that it's fast, but we have to analyze that why is it fast, or what makes the algorithm fast, or what makes it slow. Uh, so again, we'll learn about this in our next topic. Okay, so to sum up everything, data structures and algorithms are very important to computer science. So according to Donald Knuth, data structures and algorithms are a core knowledge in computer science. And according to Nicholas Worth, programs are just a combination of algorithms and data structures. So I hope you understand the importance of data structures and algorithms. In this course, we will focus more on the data structures because the algorithms part will be discussed in detail in ComSci 142 next semester. But even so, data structures and algorithms usually come hand in hand. So we also have to keep in mind that data structures don't exist on their own. There are also algorithms that use these data structures. Okay, so to summarize everything, we discussed about data structures, which are a systematic way of organizing and accessing data from the computer memory. We also discussed algorithms, which are a step-by-step procedure for performing some tasks. We also looked at some object-oriented concepts like encapsulation, abstraction, and inheritance. Okay? So that's our brief introduction to data structures and algorithms. Our next topic will be analysis of algorithms using these three things: the RAM model, worst case analysis, and big O notation. Okay, so we'll use this to analyze the performance of the algorithm. So why is it running slow, or why is it running fast? Okay, so that would be our next topic. Okay, so that's it for this lecture. Thank you, and I will see you next time.